Welcome back to the Explainer. Today we're tackling a concept that is basically a rite of passage for any serious programmer: recursion. It's an incredibly elegant, almost magical tool for solving complex computational problems. But, as with any truly powerful tool, it can also be incredibly dangerous if you don't know exactly what you're doing. So today, we're going to break down exactly how it works and how you can master it.
Okay, let's dive right into this. We've got a 6-part journey today. First, what is recursion? Then, the anatomy of a recursive function. We'll practice tracing the call stack, look at recursion versus iteration, explore some real-world applications, and wrap it all up with the programmer's dilemma.
So, Section 1. What is recursion? The core concept.
What actually happens in a computer's brain when a function decides to call itself? Well, essentially, recursion is solving a big problem by making a function call itself on a smaller version of that exact same problem, over and over and over until a base case stops the whole process. Think of classic Russian nesting dolls. You open one up, and hey, there's a slightly smaller one inside, and then another and another. The problem just keeps shrinking down layer by layer by layer. But obviously, you can't just keep opening dolls forever, right? Eventually, you've got to hit the absolute bottom. You need a solid stopping point.
Which brings us to Section 2, Anatomy of a Recursive Function, Building the Mechanism.
Let's peek under the hood at the two essential gears making this algorithmic engine run. What's really interesting here is how perfectly these two elements interact to solve our problem. First up, Step 1, the base case. This is your stopping condition, the exact moment the function finally returns a value without making another recursive call. Think of it as your emergency brake. Then, you've got Step 2, the recursive case. This is where the function actively reduces the problem and calls itself on a similar but smaller subproblem. It's the engine actively shrinking the task down, constantly driving you toward that base case.
But what happens if you forget to build in that emergency brake? Well, look at the consequences. If you miss that base case, way too many calls are made. Your computer's memory gets rapidly consumed, and eventually the whole program crashes entirely with what we call a stack overflow error. Stack overflow. It literally sounds dramatic because it is a catastrophic memory failure. You've essentially told the computer to keep opening nesting dolls that just don't exist, leading to a complete collapse. All right, Section 3, Tracing the Call Stack, Following the Math.
Let's actually look at how a computer calculates a factorial to see these mechanics in real time. I'm going to guide you step by step down these calls. Say we want to find the factorial of 4. In call 1, the function basically says, I don't know the final answer, but I do know it's 4 times the factorial of 3. So it pauses and makes call 2. Call 2 says, okay, well I need 3 times the factorial of 2. It makes call 3. Call 3 needs 2 times the factorial of 1, and boom, finally, we hit the base case. The factorial of 1 is just 1. We've hit the bottom doll. Now we sequentially bounce right back up the return chain. The base case returns 1, call 3 takes that 1, multiplies by 2, and returns 2. Call 2 takes that 2, multiplies by 3, and returns 6. And call 1 takes that 6, multiplies it by 4, and finally spits out our final answer, 24.
But we really have to talk about the physical cost of doing math this way. When we made those 4 calls for our factorial, frame 1, frame 2, frame 3, and frame 4 were all active in the system at the exact same time. Every single one of those calls adds a stack frame to the computer's memory. That's the reality of this nesting process. The computer actively holds the state of call 1 open while it figures out call 2, and so on. They literally just stack up continuously until you finally hit that base case.
Moving on to Section 4, Recursion versus Iteration, the heavyweight bout.
It is time for a classic programming showdown, the elegance of recursion against the standard iteration of loops. In this head-to-head contrast, let's look at control first. Recursion uses self-calls, while iteration relies on loops. For stopping points, recursion demands a base case, whereas iteration stops when a loop condition is met. What about memory? Well, recursion is usually higher because of that active call stack we just traced out, while iteration is generally lower. And the risks? Infinite recursion triggers a catastrophic stack overflow, while a bad iteration just traps you in an infinite loop. So the crucial point here is that recursion often trades memory efficiency for structural elegance.
Let's get into Section 5, Real-World Applications, where recursion shines. If recursion costs so much memory, why even use it? Well, let's look at its real-world superpowers. These are the situations where standard loops would just be a messy nightmare to write. First up,
fractal image creation. If you've ever seen those absolutely mind-bending, infinite repeating visual patterns, yeah, that's recursion in action, miraculously drawing smaller and smaller versions of the exact same shape. It's beautiful. Then there's traversing binary trees, where you're processing left and right subtrees with identical logic. Sorting algorithms, like merge sort. And my personal favorite, folder and file exploration. Think about it. A computer folder contains subfolders, which contains subfolders. The logic to open a folder and look inside is exactly the same no matter how deep you go. It perfectly matches the self-similar nature of recursion.
And this brilliantly illustrates the quicksort algorithm strategy, one of recursion's most famous and powerful uses. Step 1, you choose a pivot value. Step 2, you split your items into values less than the pivot and greater than the pivot. Then, step 3, you recursively sort those smaller sublists. Finally, step 4, combine the results. You're literally using recursion to divide and conquer a massive list into tiny, manageable, easily sortable pieces.
I really want this absolute core truth to sink in. Why does recursion fit here? Because each sublist is the exact same kind of problem as the original list, only smaller. This is the absolute essence of recursion. It thrives on solving tiny clones of the original problem. If that core structure repeats, recursion is definitely your best friend.
Finally, Section 6, the programmer's dilemma, making the choice.
You're the architect now, and you have to decide when to actually deploy this powerful tool. You've got to be highly strategic. You choose recursion when the problem breaks naturally into smaller, similar subproblems. You choose it when the structure is inherently hierarchical, like those binary trees or nested folders. And you choose it when the clarity and readability of your code is actually more important than strict minimal memory usage. But you also absolutely need to know when to avoid it. Avoid recursion when a simple loop solves a problem clearly. Seriously, don't overcomplicate things just to look clever. Avoid it when the input size might create extremely deep, unsafe call chains. Remember, poorly designed recursion with massive inputs will hit a depth error and completely crash your program. And obviously, avoid it if repeated recursive work makes your solution horribly slow and inefficient. Now, I want to speak directly to the high school students tuning into this explainer for their IB computer science prep. Pay very close attention here. The best answers in your exams do not just mechanically explain what recursion is, they justify the choice. To get those absolute top marks, you need to justify your approach based on suitable structure, readable solutions, and acceptable time and space costs. Don't just define the tool, prove exactly why it is the right or wrong tool for the specific scenario you're given on the test.
So, I'm going to leave you with a provocative thought for your next coding challenge. Will you choose the structural elegance of recursion, or does your particular problem demand the absolute memory safety of a simple loop? There isn't always one right answer, but knowing how to confidently weigh that choice, that's what makes you an excellent programmer. Thanks for focusing in and learning with me today on the explainer, and I'll catch you on the next one.